Hi, this is Zang from Will Cornell Medicine. Today, I would like to present our latest work, Neurodynamics on Complex Networks, which tries to combine graph neural networks and differential equations to learn network dynamics. This is a joint work with Professor Fei Wang. Here we illustrate some complex systems, for example, brain system, transportation networks, social networks, and ecological system, which consists of linked objects, namely graphs or networks. It is not only about networks. There are dynamic flows on these networks. For example, bioelectric flow on the brain, traffic flow on the traffic network, information flow, and energy flow on these networks. They are network dynamics. One fundamental question is how to model and predict these network dynamics. We try to formulate the problem of learning dynamics on graphs mathematically. We use graph to model systems, which consist of nodes and their edges, where states of nodes xt changes over continuous time t, where n is the number of nodes and d is the number of features. We want to know how dynamics change over continuous time on this graph. Once we know these differential equations, we can know the states of nodes at arbitrary time. More specifically, we can formulate this problem as a prediction task, namely continuous time network prediction, dynamics prediction. We have graphs and its node states over time as inputs, where the states are observed at arbitrary time with irregularly sampled time intervals. We want to model the dynamics on graphs by this differential equation system. Our goal is to predict the states of nodes at an arbitrary time moment. The task of continuous time network dynamic prediction encompasses the following two tasks as special cases. The first special case is structured sequence prediction. Here, inputs are graphs and its node states, which are of ordered sequence. The ordered sequences are usually observed with the same time interval, and thus they focus on order instead of physical time. Once we can model its continuous time dynamics, we can surely predict its next case steps. The second special case is node semi-supervised classification. We have graphs, its node states, and some node labels at one snapshot. Once we know how features and the labels spread on graphs, we can predict unknown labels of other nodes. Why network dynamics matters? Because it's key to understand, predict, and control real-world dynamic systems in engineering and science. However, it is very difficult to learn network dynamics of complex systems. First, complex systems usually have high dimensionality and complex interactions. For example, there are more than hundreds of nodes and tens of thousands interactions. For example, the brain, the traffic network, and the social networks. And the dynamics are continuous timed and they are non-linear. And what's more, the structural dynamic independencies are very difficult to be modeled by simple mechanistic models. Here we illustrate some examples of dynamics on graphs. Given a grid and linear dynamics, we can see relatively smooth and simple dynamics on graphs. However, the same dynamics on a scale-free network shows totally different dynamics. Furthermore, if we check this nonlinear dynamics, if we check a nonlinear dynamics on this scale-free network, we can see the dynamics are not stable anymore. It grows over time and become very spiky. Thus, how to model network dynamics is very difficult. One thread of related works are learning continuous time dynamics. The physicists propose many well-known dynamics mechanism models based on a clear knowledge of the mechanisms. The system is usually small systems with only few interaction terms. Data-driven machine learning methods are also investigated to learn dynamics of small systems. For example, sparse regression. They build a large interaction terms and select from it by sparse regression. However, this method can only handle very small systems because its combinatorial complexity of the interactions with the system is very large. It cannot handle complex systems. Another line of work is structured sequence learning. As we mentioned before, the dynamics on graphs are regularly sampled with the same time interval, and thus they focus on order instead of physical time. Various temporal GNN models are proposed. The basic idea is try to combine different RNN structures and GNNs. They can only model ordered sequence instead of continuous physical time. The third line of work is node semi-supervised classification. The defined characteristics are they are one snapshot features and some node labels on graph. Their goal is to infer labels of other nodes. Different graph neural networks are proposed, for example, graph convolution network, graph attention network, and so on and so forth. The limitations are graph neural networks usually have one or two layers and they suffer over smoothing when models are deep. They lack the view of continuous time dynamics. By explicit capturing continuous time dynamics, by spreading features and labels on graphs, by continuous time dynamics, we can get more fine-grained GNN models to capture diffusion. Thus, can we propose a unified framework to model continuous time network dynamics prediction, structured sequence prediction, and node semi-supervised classification by a unified framework? Our idea is to combine differential equations and graph neural networks. The differential equations are general tools to describe the dynamics of systems. Graphs are general tools to describe the structures of systems. GNN, temporal GNN are the state-of-the-art computational tools driven by data for linked data. Thus, how to leverage differential equations and graph neural networks. Here we show our neural dynamics on complex networks, denoted as NDCN for short. We model differential equation system by a graph neural network structures. The deep model is just an integral from time 0 to time capital T. Such a deep neural network has continuous time, continuous steps. We can also model this dynamics in a latent space by introducing additional encoding and decoding mappings. All the parameters are learned as an optimization framework with supervised information of the rounding loss over time and the terminal loss at the terminal time t. Here we show an instance of our NDCN. We model differential equations in the latent space by a simple graph convolution layer. This is a graph convolution operator. This is the parameter, and this is the learned parameters. This is a graph signal X. There are one encoding mapping and decoding mapping. We integral over continuous times to get a continuous depth model, which can capture dynamics at arbitrary time. So we can illustrate this by this framework. So this is the encoding, this is the decoding, this is the integral, this is the graph convolution. So we integral over time. We can get the arbitrary dynamics at arbitrary time t. We can interpret our simple instance of NDCN from the perspective of graph neural networks. Here we can see a graph neural layer. If we stack many graph convolution layers, we can get a deep graph neural networks. However, if we will instead of modeling the mainstream signals, we model residual signals here. We can get the residual GNN here. we can see xt1 equals to xt plus this neural convolution layer. If we make these residual signals to be infinitesimal small, and add operation becomes integration, and then we get the differential equation and the ODE-GNN. If we model this convolution in the latent space by introducing encoding and decoding layers, this is our NDCN, which is also an ODE neural networks in the latent space. Thus, in summary, our model is an ODE-GNN. We have continual layers or continuous types. We can have a real number of depths, and also we can model latent space dynamics. We can further interpret our models from the perspective of RNN or temporal GNN. For example, the simplest RNN model is just this is the hidden state base, this is the output. By introducing graph convolution here, we can get a very simple temporal GNN by combining RNN and graph convolution. If we model the residual signals, we can get the residual RNN or temporal GNN with skip connections. If we make these signals to be infinitesimal small, and then the add becomes integration, we can get the ODE-RNN or ODE-GNN. Thus, our model is an ODE-GNN, which can learn continuous time network dynamics. Also, our model encompassing temporal GNN by discretization. And also, we can encompass RNN by not using graph convolution operations. We first validated our model by learning continuous time network dynamics. The problem is given input graph and arbitrary time and irregularly sampled states of nodes, which have arbitrary time moments with different time intervals. Our output is try to predict the state at arbitrary time t. If t is smaller than the observational interval windows, it's called interpolation. If the prediction is in the far future, we call that extrapolations. Setup is we irregularly sampled 120 snapshots of ground truth network dynamics. We use the 4100, 18 for train, 20 for testing interpolation, and we use the last 20 in the future for test extrapolation. At first, we validated our model by many canonical dynamics of graphs in physics and biology. Here, we examine continuous dynamics of heat diffusion, mutualistic interaction dynamics in biology, and gene regulatory dynamics. We examine these three dynamics on different typical graphs. For example, grid, random graph, power law graph, small world graph, and community graphs. We visualize the dynamics on graph like this. We map the graphs into a grid and we plot their states over time, just as this animation. There are some baselines, but also there are application models. For example, we can model ODE-GNN without encoding and decoding layers. Another baseline is neural ODE networks, which means there is no graph diffusion layer. And also we can use NDCN without control parameters W, which is a deterministic dynamics in physics. We first learn heat diffusion dynamics on different graphs, including grid, random graph, power law graph, small world graph, and community graph. The second row is the ground truth dynamics, and the third row are the network dynamics learned by our NDCN model. We can see the same heat diffusion dynamics with the same initial conditions show different temporal patterns on different graphs. However, our NDCN can learn all of them very accurately over time. Next, we validate our model on mutualistic dynamics in biology. we found the same mutualist dynamics on different graphs show quite different temporal patterns. Some network dynamics grows very fast and show very spiky patterns like on the power law graph or random graphs. However, our NDCN can learn all these network dynamics accurately, ranging from the very smooth dynamics to growing fast and spiky dynamics. Next, we validated our model on gene regulatory dynamics. Again, we found the same gene regulation dynamics on different graphs show quite different temporal patterns. Some network dynamics grows very fast and show spiky patterns on random graphs or power law graphs, and cluster dynamics on community graphs. Again, our NDCN learned all these network dynamics very accurately over time. We validated extrapolation predictions. We measured the error by mean absolute persistent error. We run 20 times for each of 3 dynamics on 5 graphs, which is 15 experiments. For each experiment, we run 20 times. And our model achieves lowest errors and standard deviation. We first validate interpolation predictions. Our model achieves the lowest error again. Next, we validate our model by structured sequence prediction. Here, the dynamics are regularly sampled with the same time interval. We try to predict the next M steps. We compare our NDCN with temporal GNN models. We use different RNN structures, including LSTM, GRU, RNN, combined with different graph convolutions in it. Our model achieves lowest error with much fewer parameters. We can see LSTM GNN, GRU GNN, RNN GNN has many parameters. Because GRU is simpler than LSTM, RNN is simpler than GRU, we can see their parameters decrease gradually. However, our NDCN can achieve the lowest errors with very a small number of parameters than the baseline models. The last experiment of node is node semi-supervised classification. We have one snapshot of features and some nodes labels, and we try to predict all the nodes labels. The data sets are well-known Cora, Sightseer, PubMed dataset. We compare our model with the graph convolution network, attention-based GNN, and the graph attention networks. Node semi-supervised classification we can interpret in a dynamic view. Input are graphs and the dynamics of X and its features and labels. Output is to complete the features. Our model is a graph dynamics to spread features and the labels over continuous time. By spreading the features and the labels, we can predict the nodes with unknown labels. We measure our experiments as baselines by accuracies over 100 runs. We can see our model achieves very competitive results compared to complex graph convolution structure like the graph attention network or graph convolution networks. Our models captures continuous time dynamics on graph. For example, we see these graphs. We can see their accuracy first increase and then decrease. The best result is at the time t1.2, which means continuous steps and continuous time. Our models can capture 1.2 steps. In summary, we propose a novel NDCN model, which is a continuous depth graph convolution GNN, a continuous time temporal GNN, and also is a graph neural ODEs. Our NDCN is a unified framework to solve continuous time network dynamics prediction, structured sequence prediction, and node semi-supervised classification at one shot. Our model achieves good performance with less parameters. By combining ordinary differential equation and graph neural networks, Our model is a potential data-driven method to model structures and dynamics of complex systems in a unified framework. Thanks for your time. Please check our papers or our web pages for more information. Thank you.